All right. Hello, everyone. It is good to see you for another Physics Meets ML. It is wonderful to have Gavin Hartnett here. He is joining us from RAND, and his PhD was in physics from Santa Barbara, which is where I met Gavin, and he was doing work on black hole physics and the ADS CFT correspondence. But he's been pushing into other physics and ML directions in recent years as a part of RAND. And in particular, today, he's going to tell us about his work on SpinGlasses, which are complex systems that arise in condensed matter physics, and modeling them with normalizing flows. So it's wonderful to have you here, Gavin. Please take it away. And apologies in advance if I get kicked off temporarily because I'm running into some technical issues.
Okay, thanks, Jim. And let me go into presentation mode. And yeah, thanks, Jim. Thanks to all the organizers for giving me this opportunity to talk. I've really enjoyed this seminar series so far, and so I'm really happy to be having the opportunity to share some of the work I've done in the same series. Okay. And now my screen is frozen.
If you need to stop sharing and reshare, that's
maybe
that happens.
Okay. Oh, my preview crashed. Hopefully this works now.
Looks
okay,
great.
yeah. Sorry about that. Okay, so this is joint work based on these two papers here. And this was done in collaboration with Masoud Mozani, who's at Google. And yeah, if you have any questions, please, if you have any questions that don't get asked during the talk, please feel free to reach out to us over email and we'll be happy to chat about it. Okay, so the outline of the talk is I'm going to just give an introduction, motivation to what we're trying to accomplish here. And then there's going to be two sections, one based on each of the two papers I just mentioned. The first is about taking a system that is defined in terms of discrete variables and finding a continuous formulation of that system. And then the third section is about using that new formulation to build what we're calling generative SpinGlasses using normalizing flows. And then I'll talk about some numerical experiments we did, and then we'll conclude with a summary and outlook. Okay. And so, what I want to do is review SpinGlasses for anyone who's not familiar with them. And sorry again for this happening. So here's a simple expression I'm showing at the top. This is the Hamiltonian of a spin system with two body interaction terms. And so what my focus here on this talk is on classical systems where the variables are just binary spins with a plus or minus one value. And you can imagine much more complicated interaction terms like 3-body, 4-body, and so on. But for simplicity, let's just focus on 2-body interaction terms. And even with that restriction, I mean, this is a very simple looking expression, but it encapsulates a really large family of models and probability distributions. If you take the probability distribution to be the Boltzmann distribution associated with this Hamiltonian. So this includes, for example, the well-known 2D Ising model, but it also includes SpinGlasses with, which are determined in terms of the fact that this coupling matrix, this Jij, is disordered and includes frustration. So you cannot satisfy all the different bonds in the system at once, and there can be multiple metastable states. And this expression of this simple Hamiltonian actually can encapsulate really rich phenomenon such as spin-glass order and replica symmetry breaking. And so it's an interesting thing to study. And it's universal in a sense that it has connections to many different fields. So for example, it has connections to combinatorial optimization, graphical models, Boltzmann machines, neuroscience, and many others. And just to give you a sense of like the expressive power of this family of Hamiltonians, you can map it to various NP-complete problems. And so it's sort of able to represent arbitrarily complicated combinatorial systems. And so any sort of insight you have into this, whichever language you'd like to use, it can be quite powerful because it then can translate to these other fields. Okay, so that's the system we're going to be focused on. And in particular, I'm interested in SpinGlasses, and there's many SpinGlasses, but the most famous one is called the Sherrington-Kirkpatrick model. And this is a simple toy model. And so the definition of it is you take the expression I had previously, and you take these couplings to be independently and identically distributed according to a normal distribution. The mean, you can have a non-trivial mean. I just got an alert, but I don't know if that's from this. And let me, sorry, Jim, is everything okay?
Everything was good. I didn't see an alert, and all I see is there's a little, your title bar is coming up and down a little bit, but it's all fine. Okay.
Yeah, sorry, I guess I'm not very good at Zoom. Right, so you take these couplings to be Gaussian variables with in this case, zero mean and a standard deviation that scales like 1/n so that the large n limit is defined. In this case, we have all-to-all couplings. So you could have in principle a graph or some interesting lattice, but in this case, let's just take it to be all-to-all couplings, which makes this a sort of infinite dimensional or mean field model. And in my opinion, this model is really like the perfect toy model in physics because it's simple enough that it allows you to have it to be solvable, and yet it can still have really rich physics, and surprisingly rich physics actually. And so a lot of the history of the development of the field of SpinGlasses is associated with progress on this model. So at low temperatures, this thing exhibits a novel spin-glass phase, which is characterized in terms of something called the overlap matrix, or the Parisi order parameter. And just to explain what this is, and quickly, for people who don't know, you can imagine setting up the system in many different initializations and letting it equilibrate. And then you can compute these average spin configurations at each site. And so for each different experiment or realization of this, you would have the index A and B, and you can compute this pairwise overlap. And in the SpinGlass phase, this thing will have some non-trivial distribution. And so the order parameter is actually a continuous probability distribution over this order parameter of this overlap matrix. And the physics of this was really worked out initially by Parisi. And so it's kind of nice that just recently he won a Nobel Prize. The citation for the prize was more general than his work on the SpinGlass, but I think it played a big role. So that's kind of a nice coincidence. The goal of this talk is to focus on generative machine learning these types of SpinGlasses. And I'm sure all of you are aware, but just to remind you, by generative model, I mean a model that can learn to generate data from a target distribution. So this could be good examples of this are VAEs, variational autoencoders, restricted Boltzmann machines, normalizing flows, or GANs. And we're going to be focusing on the normalizing flow angle. And these models are going to be machine learned. And in the case of SpinGlasses, what this means is that we have this disorder realization, and in some cases an instance graph or a lattice, which could itself have fluctuations or be random. And the generative model we're going to train should be tailored to the system of interest. And so it should incorporate the information about the specific problem instance we have in front of us. And ideally, the generative model would then be more powerful than more common sampling techniques that wouldn't incorporate that information. And in terms of this general trend, it exists beyond applications to SpinGlasses, and it's received a lot of attention recently. And so I think probably the most promising and exciting direction has been in lattice gauge theory. And in this seminar series, there's been a few excellent talks on this topic by Fiala Shanahan and Danilo Resende, and perhaps even others. And there's many papers on this, and I'll just cite one to give an example. But that's been very interesting, and the idea of incorporating symmetries in the problem as well. In terms of condensed matter applications, there's a few papers on that as also, and two particularly notable ones are shown here. As far as we were aware, the work I'm going to describe today was the first one applying this approach to SpinGlasses. And I would argue that SpinGlasses are really an important and challenging application of this line of work because of the expressive power I was discussing earlier, the fact that they can encode arbitrarily complicated optimization problems. And so it's a double-edged sword, because on the one hand, certainly you don't expect to solve NP-complete problems in a very simple way using normalizing flows. On the other hand, if you can make progress on problems associated with SpinGlasses, it's a very useful and powerful result that could be applied in many other areas. Okay. And so, yeah, as I said before, we're going to use normalizing flows for this problem. And in those talks I mentioned before, I think gave nice introductions to normalizing flows. So I'll just kind of quickly review it in this one slide. And so the idea of a normalizing flow is to learn a transformation from a simple prior distribution to some target distribution. And in the case of normalizing flows, this transformation should be invertible. So it can go forwards and backwards, and it should be this should be able to be applied efficiently. And that's actually like a very important constraint. And the way this works is at a really high level is you take the general normalizing flows composed of multiple layers of simpler functions. And so you simply compose these together. And each of those layers is invertible and efficiently invertible. And there's many architectures at this point that accomplish this. The one we used is a quite popular one called real non-volume preserving normalizing flows. And just to give a schematic picture of what it's doing, I shamelessly stole this nice figure from Lillian Wang's nice blog post. And what all it's showing is that on the left-hand side, you can sample from a simple Gaussian, although it doesn't have to be a Gaussian, it could be a uniform distribution. And then you subsequently apply these different layers, which transform that sample. And if you track how the overall probability distribution transforms, you get this more and more complicated thing that can be multimodal. And at some point you terminate, and that's your sample from the flow distribution. And you can just as easily go in the reverse direction to start with what's called X and end up with Z, where Z is the latent variable or the variable distributed according to the prior. Okay. So what I want to talk about now is in order to apply this approach to SpinGlasses, what I need to do is convert the discrete SpinGlasses into some sort of continuous representation. And the reason for this is because normalizing flows assume a continuous distribution. The entire framework is based on finding a continuous map from one probability distribution to another. But the SpinGlasses, as I've introduced them, are discrete systems, so that poses a problem. And admittedly, it's a bit of a contrived problem because, well, there's many points to mention. So first is that continuous SpinGlasses exist. In fact, quite famous ones, of which a lot is known. Also, there are many extensions of normalizing flows to discrete distributions at this point, and I'm probably missing some, but here are two that I know of. But nonetheless, our approach was to stick with the discrete SpinGlass, the well-known and perhaps most famous model being this Sherrington-Kirkpatrick model, and to use something known as the Hubbard-Svirtanovich transformation to convert it into a continuous formulation. And the Hubbard-Svirtanovich transformation is of course like a standard technique in physics. I think it dates back to the 60s or so, but it's been applied to these types of discrete distributions like restricted Boltzmann machines and so on in these two papers, with the goal of improving the sampling of these things. And so we're going to follow those approaches, and I'll describe in more detail in the next few slides, but the basic idea is to take a +1, -1 variable and convert it to something that's a real valued variable. And just as a final point, other transformations exist. For example, there's this paper out of Los Alamos where a more complicated transformation was introduced. Okay, so the basic idea is we want to introduce a continuous variable, and that provides an alternative formulation of the system. And there's different ways of describing this. I'm going to sort of follow the statistician's approach and talk about conditional probability distributions, but the physics audience would probably be more familiar seeing this in terms of the Hubbard-Svirtanovich transformation, and they're identical. They're just different ways of sort of introducing it. So what you do is you introduce this variable x, and you declare that the conditional distribution p of x given s should be a Gaussian. And the mean of the Gaussian is going to be centered around the particular spin configuration, and there'll be a covariance matrix that will be temperature dependent. So low temperatures, the covariance will be really, the Gaussian will be really tightly centered around that spin, and at high temperatures, it'll sort of be spread out. And importantly, this isn't an isotropic Gaussian, it's a Gaussian with some ellipsoidal shape. And that shape is given by this inverse of the coupling matrix. And it's not just a standard coupling matrix, it's a shifted coupling matrix. So we're introducing this thing called J tilde. And here the overall shift is chosen to make this thing invertible, because it might not be invertible depending on the problem you're interested in. And so you shift it so that all the eigenvalues are positive, and then you can define this covariance matrix. And the beautiful thing about this particular choice of the distribution is that if you try to compute the marginal distribution over just x, you can easily do that marginalization and get an expression that's not that complicated for p of x. And just to give you kind of like an intuitive sense of what this is doing, I'm showing here a really low dimensional example for a really simple coupling matrix that's isotropic. And you see that we're just essentially throwing down a Gaussian on each of the spin configurations. Okay, and you have, to write it out in equations, we can sort of have an analogous way of discussing both distributions, the discrete and the continuous. Both of them are described in terms of Boltzmann distributions, where there's a Hamiltonian and a normalizing constant called the partition function. The one distinction between the two that's really important is in the continuous case that we have a probability density. So you have to be careful with how these things transform under changes of variables. And so when you, for example, when you will apply the normalizing flow, there'll be an overall Jacobian factor we have to take into account. But otherwise, it's sort of an analogous way of representing the two distributions. And both of these representations are able to encode really complicated energy landscapes. And then to go back and forth between them, we can use relatively simple conditional distributions. In the one case, it's a Gaussian, as I've already mentioned. And in the other case, to go from continuous back to discrete, your distribution factorizes over the spin sites, and it's just a simple binary value distribution like this. Okay. So I said that the covariance is temperature dependent, and there's sort of an interesting consequence of this that is obvious when you think about it for a minute. And so the fact that we're obtaining this Hamiltonian density over the continuous variable by marginalizing the original discrete variable means that this Hamiltonian density is temperature dependent. And so the shape of it depends on temperature. And at high temperatures, all the different Gaussians sort of blend together and overlap such that there's just a single maxima in your energy landscape, or sorry, a probability space, and or a minima in your energy landscape. And at low temperatures, you have the situation I said earlier, where you have multiple modes centered around each of the spin configurations. And so there's a temperature at which the picture changes from a convex to non-convex energy function, or a concave to non-concave probability density. And that temperature was worked out in this paper by Zhang et al. And it's really simply just given in terms of the largest eigenvalue of the shifted coupling matrix. Okay, so that's interesting, but probably not surprising when you just stop and think about this for a moment. But it has an interesting consequence. So whether or not a distribution is convex, or not the distribution, but the energy function, that actually has really important practical implications. So for example, if your energy function is convex, it means there's certain sampling methods you can use that you wouldn't otherwise be able to use. And some statisticians have also recently proved that other algorithms, like based on Langevin diffusion, have provably fast mixing times when you have this convexity property. So this transition seems to have some sort of interesting and tangible consequences associated with it. And you might expect that it's connected to the standard SpinGlass transition that exists in the discrete formulation. And the reason I say that is because SpinGlasses should be hard. They should be hard to sample from, hard to optimize. And so you might think that these two transitions are related in some way. And in that first paper, we sort of looked at a bunch of different examples. And in every example we found where a icing system had an interesting phase transition, that phase transition happened at a lower temperature than the convex transition. And so as you lower the temperature, you first cross this convexity threshold and your problem becomes non-convex and you lose these provable guarantees. And then as you lower the temperature further, you'll cross whatever phase transition the system might experience. And in the case of a SpinGlass, it'll exhibit an exponentially large number of these metastable states. The other weird wrinkle in this story is that this convexity temperature depends on this shift parameter delta, which has some degree of arbitrariness associated with it. So it's a parameter you've introduced when you do this Hubbard-Svirtanovich transformation, but there is a minimum value that is unique. So it's not completely arbitrary. And the interesting thing is that even if you chose it to be the minimal value, this phase transition temperature will always, it seems, be lower than that. And so we expect that this phase transition temperature will always, for any SpinGlass transition, be lower than the convexity temperature, but we haven't proven this, or we've only sort of looked at this for a few examples. And so that's something that we're interested in pursuing further. Okay, so with that lead up, now I'm going to switch to talking about generative SpinGlasses, which, that's the main focus of the talk. And so all that came before was sort of necessary machinery that was needed to put the SpinGlass in a formulation where we could actually apply normalizing flows to this problem. Right, so the idea is now that we have this continuous probability distribution, P of X, that's the continuous SpinGlass, we'd like to model it using normalizing flows. And so the idea is that we want to build an approximation to this distribution, and it'll have the nice property that it'll be simple to sample from. So the idea is that the SpinGlass should be hard to sample from, at least at low temperatures. But the way this normalizing flow is constructed, it's easy to sample from the flow. But the question is, the flow may or may not be a good approximation to that distribution. So that's the general problem in front of us. To remind people how this works, like I said earlier, we have a latent variable, which is distributed according to a simple prior, in this case, a Gaussian. And to sample from the flow, you sample from the prior, and then you do a forward evaluation of this normalizing flow, and that gives you X. And this process implicitly determines the probability distribution over X of your normalizing flow. I'm using the subscript G to denote that. And in order to work out what that is, you can just use the standard change of variable formula for a probability density. And there's this standard Jacobian factor because you have a density and not a scalar. In our work, we found it helpful to think of the normalizing flow not just as a distribution, but as something parameterized in the same way as the normalizing flow, as the SpinGlass. And what that means is it's sort of just for presentation purposes, it's nice to introduce an associated Hamiltonian density for the flow. And this is what it looks like. This particular form is just simply due to the fact that we have a Gaussian prior that we're then transforming according to this change of variables. Okay, and actually we can do this for all the discrete layers of the flow, because like I said, the flow is composed of multiple layers. And so you can actually sort of write down a Hamiltonian density for every single layer of the flow. And in this case, we have a discrete sequence, but if we had used an approach like neural ODEs, for example, it would be a continuous sequence. Okay. So of course, the main difficulty here is going to be in training these things. So it's not difficult to set up a normalizing flow that you then want to use to model some distribution. But if you wanted to do a good job approximating that thing, you have to successfully train it. And in our case, we have the luxury of two primary methods of training the flows, and then there's a few variations we could consider also. And so the first approach is going to be familiar to people who are applying normalizing flows in more standard machine learning contexts, and it's based on the forward KL divergence. The idea here is that you generate a bunch of training data from sampling from your model. In our case, we generate this data using parallel tempering Monte Carlo Markov chain approaches. But in a more traditional machine learning case, this would have to come from whatever data set you acquired. So you'd be limited by your ability to acquire the data. In our case, we have an unlimited data generator with the caveat that it's expensive because we're using Monte Carlo on a SpinGlass that could be potentially very hard to sample from. Once you have your data, you train it by minimizing the forward KL divergence, and this corresponds to maximizing the log likelihood. And the KL divergence, the argument of the KL divergence is not symmetric, so the order of the two distributions matters, and just by convention, this particular choice is called the forward approach. You could also have considered the reverse approach. And normally this approach is not available to people because if you work out what it is in terms of an expectation value, it's an expectation value over the prior, the latent variable z, and it depends on a difference between the true probability and the target probability, or in this case, the true and target Hamiltonian densities. And in most practical applications, you don't actually know the true distribution that your model, the data was generated from, but in this case, we do. So this is a really interesting loss function to pursue because, as you see, the overall expectation value sitting in front of the loss function it's a very simple one to sample from. You just have to sample a bunch of independently and identically distributed Gaussian variables. So that's essentially trivial to do, and you can do this as long as you'd like. You don't need to do complicated Monte Carlo sampling, and you don't need to go out and obtain an expensive data set. So for physics-based approaches, this is an interesting loss function to pursue. Okay, and we're going to consider both of them.
Gavin, just a quick question.
Yeah.
So you can do this anytime you know the target density, basically. You know the target density, and you're just making sure that the density induced by the flow matches what you expect for the physical model.
Yeah. And because both of these loss functions are based on the KL divergence, you're essentially looking at the difference between the two different densities. But in one case, you're looking at it on points that were sampled from the first one, and on the other example, you're looking at them at the point sampled from the other distribution. And the idea is that the flow is sort of trivial to sample from. Yeah. And yeah, exactly. You can, if you feel like you need more samples, it's no problem to get more of them.
Yes, got it. Yep, thank you.
Yeah, and then there's these overall constants you might be interested in computing, which, so in our case, we have the Hamiltonian density. That's simple. In principle, you could try to work out what the normalization constant is, this partition functions, which could allow you to plot the exact KL divergence and not the shifted version of it. And that's, in principle, you can do that with the SK model, although it's a little tricky because you have to really get into the details of Parisi's replica symmetry breaking solution. But that's another thing we can do in this case that normally you wouldn't be able to do. And in a general SpinGlass, you wouldn't expect to be able to do that either. Okay. And this might be a good time to ask if there's any other questions. No? Okay. Good. So this is really sort of like the first set of results in what we think will be a longer effort. And in that vein, we decided to look at a rather simple model, the SK model. And the reason for this is that, like I said earlier, it's simple to describe, but it's rich enough that we can it can exhibit really interesting physics. And a lot of this is analytically very well understood. So it's a great model to sort of benchmark your approach against. And in the future, we'd like to graduate to more complicated systems. And so for this, we're looking at n equals 256 spins, it's just somewhat arbitrarily chosen. And it's a rather small number of spins, but because this spin glass has all-to-all couplings, you essentially have to square that and divide by 2 to get the number of independent bonds. So I wouldn't say it's a really large model in terms of the parameters you need to describe it, but it's not as small as you might think just based on the number of spins. And yes, it's a very complicated problem because at low temperatures, this thing exhibits an exponentially large number of metastable states. And in our experiments, some of the results might depend on the particular disorder realization. And obviously, we don't want that. So we've averaged over 10 different disorder realizations. And we looked at a range of temperatures. And importantly, the range we chose existed on either side of these two transitions we identified as being potentially interesting. Like for sure, the spin glass transition is interesting. And there's also this convex, non-convex transition that happens at a temperature 4 times as high as the spin glass transition. Okay. And we trained flows using both the forward and reverse approaches. And as I said earlier, there's more complicated things you could do, like a hybrid approach or an approach where you use the symmetrized KL divergence, but we just looked at these two simple extremes. And in the case of the forward approach, we have to generate the training data. And in this case, we did it using parallel tempering Monte Carlo Markov chain, also known as replica exchange, MCMC. And yeah, we used 4 different layers for the normalizing flows. And I have some more details on this in the backup slide if you're curious, and you can find them in the paper, the second paper. Okay, so the first thing to show is the loss functions for both approaches. Really, I'm just showing this to sort of, show you that we actually trained some models. There's not a whole lot of interesting lessons to be learned from looking at these, aside from the fact that the loss function is temperature dependent. At low temperatures for the forward KL case, you get some significant variation in between different batches. And in the reverse case, there's a really steep fall off in your loss function after just about 100 training iterations. What we really want to do, of course, is to make sure our model is doing a good job representing the key physics of the spin glass, and then to eventually, which we're not going to do in this talk, go beyond that and use these things to improve your sampling or optimization. And so to take some steps towards that evaluation of how well the model is doing, just looking at the loss function, seeing that it goes down is certainly not enough. And so there's some more interesting things we can look at. And so the first of these is the overlap distribution. And as I said in the really beginning in the introduction of the talk, the overlap distribution is the unique order parameter that sort of distinguishes spin glasses from like a more standard ferromagnetic icing system. And so this is a natural thing to look at to make sure, as a check at least, that our model is capturing the key physics of the spin glass state. And so in order to do this, operationally, what we do is we sample many states from our normalizing flow, and those will be the continuous X variable. And we can convert that to the original discrete variable using the conditional distribution. And then you can compute these overlaps by, for every pair of states sampled, you have, like, let's call them A and B. You can then compute this this sum where you multiply the two spin configurations together and you just sum over the different sites. And you can build up a histogram of the distribution of these of this thing. And of course, it'll depend on the temperature because there's a spin glass transition at temperature equals 1 in these units. And so looking at this sort of from the bottom right and then going to lower temperatures, at high temperatures, both the forward trained and reverse trained flow agree pretty well with the discrete parallel tempering data we generated. And this is sort of what we would expect, that in the paramagnetic phase where there is no spin glass order, the overlap should just have a delta function peak at q equals 0. But that's in the infinite n limit, whereas here we're looking at finite n. So you'd expect a sort of, something that looks like a single mode distribution peaked around q equals 0. At lower temperatures, for example, right at the phase transition, the forward train flow and the Monte Carlo data are still in fairly good agreement, but the reverse is starting to show some troubling signs where it's disagreeing from the right answer. Even more worrisome as you go to even lower temperatures, well, the forward train flow and the Monte Carlo data are doing the right thing, which is at least qualitatively the right thing. They're becoming a whole distribution with these two peaks and a finite value of finding something in between, which is what the theoretical answer is. That if I were to show that the value that Parisi calculated, it would be two delta function peaks at a maximal and minimal value of q, and then there'd be some interpolating U-shaped function in between. So it sort of have this like U-shaped distribution. And the forward train flow and the Monte Carlo flow data is doing a good job representing that, but the reverse flow is completely failing to capture this property. And this failure gets more extreme as you go to lower temperatures. And
Gavin,
so,
it's already pretty bad by the time you hit the SpinGlass transition at 1.0.
Yeah.
And it's really good at 1.4. Does it start, I mean, is it sort of a continuous development of badness between 1.4 and 1.0, or is it really sharply, does badness sharply develop at the SpinGlass transition?
So what we think is happening, and I think most people would probably be unsurprised by this, is that the reverse train flow is suffering from mode collapse, which is like a known weakness in that loss function. So that loss function has the benefit that you sort of have this infinite well of data to draw from. So it's like very useful in that sense, but it has this unfortunate property that it tends to find like a particular mode just due to the random initialization. And then during training, it sort of becomes attached to that mode. And so the fact that the problem is getting worse at lower temperatures, I think is completely consistent with that, because at lower temperatures, you have more and more modes opening up and they're becoming more widely separated. And so if your normalizing flow is sort of focused on a single mode, which is something we did check and verify, then you would sort of expect this picture to happen. Yeah,
so the exponential number of ground states at low temperature that emerges is sort of difficult from a mode perspective.
Yeah, and I think it would be difficult even if it weren't exponential. I mean, because that exponential property, I think, is unique to the SK model, and there's other SpinGlasses where it has a slower growth. But just the fact that there's many modes, I think any reversed approach, unless you do something to ameliorate it, would suffer from that.
I mean, what I would have said before you showed these plots at all is just that because you're training on MC data, you're going to have at the various different temperatures sort of trustworthy sample diversity relative to just taking some generative model and hoping that it gets the right diversity at some fixed temperature. Is that the crux of the issue that you just?
Yeah, basically. I mean, so the sort of conundrum we're confronted with is that the forward train flow, even though it's doing a fairly good job, it can only do as well as the original Monte Carlo data you've supplied it with. Yeah. And as I said earlier, like that's a hard thing to do. Like the idea was to sort of use the reverse approach to somehow improve the situation and have something that was better than the original, like the raw parallel tempering data on its own. And what this is showing essentially is that that's failing. Like you can't just use the reverse approach. And at the end, I'll talk about some alternatives where you maybe take the reverse and combine it with something else, but just on its own, it's insufficient to sort of solve that problem.
Did you train the model at different temperature? Do you need to retrain the model at different temperature?
Yeah, and that's another issue. Ideally, you would like to have a model that like you train it for maybe a handful of temperatures, but it's the same model. In our case, for every different temperature and every different disorder realization, we have a different flow.
I see. So I think in Leiwan's paper, they propose that you can basically keep lowering the temperature while you're training the model using the using the reverse method. Then it can partially avoid the mode collapse. because you have a continuously evolving distribution.
And which paper was this?
I mean, the paper you cite.
The Li and Wang one?
Yeah.
Okay. Yeah, the other thing that's
And also this
Yeah.
is like icing symmetry breaking. So maybe there's also other ways to try to symmetrize the distribution in order to avoid at least this obvious Z2 symmetry breaking mode collapse.
yeah,
But
there's
it doesn't help other type of mode collapse.
Yeah, that's a good point. So I didn't mention this, but there's ways of making your training like Z2 symmetric. So symmetric with respect to spin configuration, and then minus that spin, just where you flip all the spins. And we did this, but even with that trick, there's still this issue that the flow itself is not symmetric under that Z2. And so there is a Z2 symmetry breaking that that's actually one thing we're doing right now that you'd like to incorporate. But even if you incorporated that, of course, that's just a Z2, whereas here we have a large number of metastable states. And so there's no symmetry that takes you from one state to another state. But at least it would take into account this partitioning of the states in terms of that Z2 symmetry. Yeah, so that'd be interesting to see what happens when you incorporated that into the flow. And that's sort of a baby version of the thing that the lattice gauge theory people have been doing, which is making their flows equivariant with respect to these continuous Lie groups. So in this case, it would just be a simple Z2, but I think that would be a good thing to do. Okay, anything else, or should I go on?
This is great, keep going.
Okay. Okay, so that's that's the overlap distribution. This one is a really interesting property of SpinGlasses that, so what I want to talk about now is a different property that SpinGlasses are known to exhibit theoretically. It's a really famous result and important in sort of the early days of developing the theory of SpinGlasses. And this is, it's known as Ultrametricity. And so the physics of this is that, and this is sort of connected to this exponentially large number of states and the thing we were just talking about, which is that as you lower your temperature, you get this hierarchy of pure metastable states. And so a little cartoon diagram of this is depicted on the right, where at some temperature you have, in this case, just a single mode, or maybe this is zoomed into a single mode. And then as you lower the temperature, you get this sort of like birth process that produces new states from that parent state. And it proceeds in this way so that you get a hierarchical structure or a tree-like structure on your space of states. And the fact that you have this tree-like structure means that if you were to think of these states as like comprising a metric space, and you think of the distance they would obey, that distance for any metric space, it should obey the triangle inequality. But in these ultrametric spaces, they obey something stronger called the ultrametric inequality, and it's shown here. And essentially what this means is that if you were to, one consequence of this is that if you were to look at triangles in the state space, they're all either going to be equilateral or acute isosceles. And so that's like a really non-trivial constraint that your distribution or your generative model should satisfy. And just because your model satisfies a set property doesn't mean you've perfectly captured the SpinGlass, but it's a really important constraint. And anyways, if there's, as a side point, there's this wonderful review by Ramal et al. on applications of ultrametricity to physics. So if you're interested in this, you might want to check that out. Okay, so we can investigate to what extent the trained flows exhibit ultrametricity. And we might expect that the forward case does a fairly good job given the results of the previous slide. And we would expect that the reverse approach does pretty bad. And that's what happens. And so there's a few ways to do this. One way that I did in an earlier paper that I don't think I was the only person to sort of make these plots, but that's the first place I figured it out or thought of it was what you do is you sample 3 different states, so triplets of states, A, B, C, And this, you can think of this as forming a triangle in your state space, and you can compute the three distances. Like, for example, let's take the Hamming distance between all these states. And to make this useful, we can sort them according to like the smallest and to the largest value. So I use the word min, mid, and max to denote this. And then you can take the differences of the largest distance to the middle distance and the middle distance to the minimum distance. And you can plot the distribution of these side lengths in 2D plots. And you get things that look like this. And so because all the triangles in an ultrametric space are either equilateral or acute isosceles, what that means is that all the probability densities should be clustered around either the origin, which corresponds to equilateral triangles, or it should lie on the x-axis, which is acute isosceles. And the left two plots do that. That's the Monte Carlo data and the forward KL generated data. And you know, this is sort of like a qualitative comparison, but the plots are certainly qualitatively similar. And if you look at like what fraction of states are in the equilateral mode versus in the acute isosceles mode, that ratio is 75%, which agrees with the theoretical value that was quoted back in, or calculated back in the 80s. And so that's a great check on the forward trained flow, that, you know, the flow is able to preserve this topological structure in the samples that you've generated from the SpinGlass. In the reverse case, there's a dramatic failure. All the triangles are equilateral, and you get this sort of, you have a bunch of these different modes, but they're all really tightly clustered at the origin. So that's another indication of the extreme mode collapse that the other plots were exhibiting. Okay. Any questions on that?
So I think to me, the basic result is clear. Are you gonna, but I mean, I think all of us probably hope that something like the reverse KL works at some point, just because it's nice to not have to run the Monte Carlo.
Mm-hmm.
Are you gonna comment on that at some point, or?
Yeah, so like I said, this is sort of preliminary work, and like in the results in the paper, it's just a failure. I mean, I wish I could say it worked or there's some way of making it work, and I have nothing to say on that. There have since been some works that have used this to success, but they were either using new approaches that we haven't tried yet, or they were applying them to really simple systems. And so, yeah, it's a little, I cannot say that the reverse approach can work on this problem, but I think it's, I would say, an open problem still. And so this work is sort of like demonstrating that the forward approach, you know, at least it can work and capture these sort of interesting properties of the SpinGlass phase. And the reverse approach, it's sort of a negative result in that the reverse approach fails in a really dramatic fashion. And yeah, it leaves for future work this question of whether or not the reverse approach could be combined with something else to be useful.
Okay. Just to ask a lingo question, when you talk about self-supervised learning, this is what you mean by the reverse KL approach, in the sense that
yeah, I should have mentioned this. I'm sorry. Let me go back. So for sure, the self-supervised terminology for the reverse approach comes from the fact that the model is sort of supervising itself, in the sense that the training data is being generated from the model. On
the fly, that's right. Yeah.
Yeah. This might be a matter of personal choice, but you could also, and this, you know, argue that the forward approach is also self-supervised, in the sense that, you know, we're also generating the data from the model itself. But in this case, that's available to us because we know the true probability density.
Right.
So in a weaker sense, I guess you could argue that's self-supervised, but for sure, the idea of the reverse one is that.
Yeah. Good. The forward KL is self-supervised by the statistical model itself, in a sense, whereas the reverse KL is self-supervised by the neural network and the flow generated.
Yeah, that's a great way to. Yeah, that's a great way to put it.
No, I understand the lingo now. I just wanted to make sure I got it. So just one more quick question. So I mean, in some sense, what you're saying there's work in progress, but hopes of using this neural network level self-supervision to accurately sample complex energy landscapes I mean, this you have to worry about mode collapse until you have better techniques.
Yeah, and I had one more thing outside of numerical results I was going to show about sampling the internal layers, but since there's only 10 minutes left, and since this is where the questions are going, maybe I'll just skip to this, my last slide, which is, so the ultimate goal is to use the generative model to improve sampling and optimization. And I just want to be really clear, like we're not doing that with this work. We hoped to, but we sort of figured out that the problem was a lot more intimidating than we initially realized. And so what we did is we explored these two approaches. One of them failed miserably and the other did a good job, but it's not immediately useful for this task, which is the forward approach. There's a few interesting avenues to pursue, but in order to have them work, you want to fix this mode collapse problem. And so one thing that's really interesting is this flow MCMC approach that pioneered by this paper by Albergo and then developed by many other authors. And they recently released a paper extending this to like lattice gauge theories with many vacua. And so I think that might be the most promising approach that we might find useful here. And I have not yet looked into seeing how we might incorporate that. And then there's also this idea of using the flow you've trained in the like the latency, using the successful flow you trained to improve Monte Carlo sampling by doing accelerated Hamiltonian Monte Carlo and with respect to that latent variable Z. Although we did actually try this and we sort of saw no improvement even for the forward trained flow. And so that still is, like I said, like a work in progress. But yeah, I just thought I'd skip to the end just to give you a sense of like the big picture and where it's going.
Great, thanks. And the many metastable lattice QCD paper is the one with many topological sectors. Is that the origin of the many metastable states? Yeah,
I'm mad at myself because in an earlier version I had it cited and I guess I changed it. I believe it's because of what you just said, but yeah, I'm not exactly sure.
Okay.
It's been I looked at it briefly and then I thought like I flagged it for future interest.
From maybe a year and a half ago?
Yeah, or no, very recently actually.
Oh, very recently. Okay, then it's interesting. Yeah. I'll take a look, thanks.
Yeah, I could actually send it to you afterwards, but I'm sure people in the audience are aware of it too. Okay, so yeah, maybe I'll just end there and take any, if there's any further questions.
Yeah, so I have a question. So regarding the reverse training, this is something I've actually used successfully for basically modeling probability distribution in high energy physics. And so one of the things, so there's basically two issues, right? So the first one you mentioned, which is that when you're not properly initialized, then it's hard to sample in a way that kind of feels where the function is important, right? Mm-hmm. And then there's the second thing, which is you're also chasing a moving target, which is that you generate the data and then you're trying to optimize it, and then you change the way you optimize the data and you go again, right? And this is something in reinforcement learning that was causing issue, and this is why there's this method called deep Q learning, in which you freeze the model that you sample from, and then you train a secondary model, and then you update the model you sample from only infrequently. And so this is something we actually found was really helping for this type of reverse approach. So you need to sample from a frozen model, and so I don't know if this is something that you've heard about, but
not this approach to deep Q learning, but maybe if you have a paper or something, you could send it to me because that sounds interesting.
So basically the idea is you freeze your model, you sample from it, and then as you change the model that you're training, you keep the same data, and you just need to reweight your loss function to correct for the shift in the PDF between the sampling and the training.
I see. Interesting. Okay.
And so
oh, sorry, go ahead.
Yeah, so this we found was really helpful. And the other thing you can do is is to first sample with your Monte Carlo data with limited amount of data, and then do the switch to reverse training. Because once your model is decently initialized and has some feeling of the modes, then you can switch to sampling from itself, and this is also
Okay, interesting.
really a way to nicely fine tune it, basically.
Yeah, because I didn't talk about this in this talk, but like we've tried some things where you use a combined loss function that involves both the forward and the reverse, and what we're seeing is that the reverse always sort of pollutes the training process by forcing you to have mode collapse, and so maybe something like what you said is a way to avoid that. Yeah, thanks for that. And I see Uros, you have a hand up.
Yeah, hi. So I have a more basic question here. Usually for Ising models, we think of them as being, infinite systems, which you can model with, low n, but then you send n to infinity. But more importantly, they are translationally invariant. They have this translational discrete equivariance. And here, if I understand correctly, you are talking more like a fully connected, where this Jij is mixing up. It's completely random, regardless of the distance between the spins.
Exactly. Yeah. And so it's there's no translation invariance or any sort of, there's no invariance whatsoever. And the fact that it's a all-to-all is what makes it, sort of, and that you have Gaussian bond strengths is what makes it solvable. But the sort of ideal application of this would be to apply this to problems that are encoding, like, for example, like the combinatorial optimization problems I was mentioning earlier, where you wouldn't have, translation invariance, but there would be some sort of interesting lattice and configuration of the bond strengths that might encode some sort of like, optimization problem of interest, whether it's, whatever it is, like, could be graph partitioning, could be even traveling salesman has been studied using these types of spin glasses. So ideally it would be applied to something with some sort of interesting structure. And the SK model sort of has, completely random structure.
Right, but so this doesn't have a physics analogy where you would send n to infinity at all, because
it does have a large n limit. Yeah.
No, I know, but what is the physics analogy? I just don't see the situations where you have equal coupling strength regardless of the.
Do you mean like what type of real world magnetic system might this be?
Yeah.
Okay. Well, I don't think I can answer that question well, but there's a really great series of I think it's from Physics Today or Physics Magazine, these articles by Philip Anderson sort of talking about the historical development of the spin glass field and how, so initially, a little bit of the history is that initially there were these experiments that were surprising people with how they were, the way the data was looking. And so they introduced something called the Edwards-Anderson model, which does have this type of translation structure you're talking about, where they had like a square lattice, but the bonds were disordered. And they initially were working on trying to solve that model, but it proved too difficult. And so the SK model is like the second toy model that they introduced as a further idealization of that, intended to make theoretical progress on this problem, which they made a lot of progress on the problem. So yeah, the SK is sort of like a mean field version of a more interesting system.
Okay, fine. I guess where I'm getting with this is, are these problems without translation equivariance of interest, right? I think you're saying yes, although you're also saying it's a toy model, so.
No, so the SK model is a toy model, but yeah. I would argue that they're of extreme interest because of their connections to, these combinatorial optimization
other
problems
and other things that are not physics. Yeah. Okay.
Yeah.
I mean, this is a major area of study in complex statistical mechanical systems. And I mean, Gavin, you know more than I do, but there's many different physical systems in principle that they map onto, right?
Mm-hmm.
Obviously the main objective was to try to get something close to the target distribution with respect to the toy model. Did you guys ever think about, if there was some perturbation of the Sherrington-Kirkpatrick model that you wanted to consider with some other physics, how you might learn and optimize on that? Or was that too much to hope for, given that the reverse KL was, well, I guess the forward was good enough as it was, but did you think about trying to optimize on different things? Perturbations of the SK model that might be interesting for physical reasons?
Oh, for physical reasons. We did not think about that. Yeah, we didn't think about that. I mean, there's lots of like models you could imagine applying it to that whatever your favorite model is, you might want to, apply this approach to. But yeah, we essentially wanted like a simple model that we knew a lot about. And so, when things started to go wrong and we could easily sort of compare with the known theoretical answer. And also, the SKML is like a very difficult problem. So if you, in terms of the optimization of it, so if you can sort of make progress on that, it's a great sign that this approach will be more widely useful. But yeah, as I said, we had pretty, the reverse approach was a negative result. And yeah.
Yeah, I see. Right, and yeah, that answers my question. Are there other questions out there for Gavin? Was there were there a couple words you might want to say on the slides that you skipped, since we sort of close this conclusion and big picture stuff?
Okay, yes. And okay, so this, I think this is kind of cute. I'll leave it up to you to decide if this is interesting or not, or whether or not it's surprising. But just as a further way to diagnose what the flow is doing, you're essentially interpolating from a simple Gaussian prior to something approximating the physical distribution, right? And so you should have if you think about it, you should have a sequence of these distributions that, like in that picture I showed from Willy and Wang, where you start with a Gaussian, you get something increasingly more complicated. The same should be happening here, except this should give you some interesting trajectory in quote unquote theory space, where the models are sort of approaching the model of interest. And so I just have a few slides showing the same set of plots I showed earlier, but now like opening up the normalizing flow and looking at the internal, these quantities for the internal layers. And so like here I'm showing the overlap, and the overlap of the Gaussian prior is peaked around Q equals 0, which would correspond to the paramagnetic phase. And then as you lower the temperature, you get this bimodal structure, and it's sort of the modes separate, move out to plus and minus 1, which is what happens at really low temperatures. And then at higher temperatures, you get a kind of a modification of that. And then of course at high temperatures, when the final target distribution is in the paramagnetic phase, all the internal layers are giving you just this kind of trivial overlap distribution. And right, you can do the analogous investigation for the Ultrametricity, and you can observe this interesting ultrametric structure. I think this is cool. You can see the ultrametric structure emerge as you go through the flow, where initially all the triangles are equilateral, and then there's this mode that pinches off and becomes the acute isosceles modes. And so you can sort of see how ultrametricity emerges halfway through your normalizing flow. And yeah, that's it. But that's sort of like a tangent to the main points, which is why I felt we could skip to the end.
Wonderful.
Yeah.
That's great. All right. Any last questions for Gavin? I have one more. Maybe you already answered it. What's up next? I saw these papers in early 2020.
Yeah, they're a little old, and the work I've sort of put on the back burner. But we're trying to, the thing I really want to do is this flow MCMC. But in order to do that, like I said, we need to really tackle this mode collapse problem. And there's been some approaches by the lattice people on that. So I think whichever approach we use, I think that's the kind of the next step. And once we unlock figure that out, it unlocks a bunch of interesting things we can do in terms of actually getting these things to be useful for various like applied problems. And then I've also been thinking about applying this to the BMN matrix model. And I'm kind of curious how that, but I have no reason to suspect that would work until we fix this mode collapse problem, because that also has this complicated vacuum. Well, it's complicated vacuous structure. It's not disordered, but it is, there is a large number of distinct vacua. So I wouldn't expect it to work unless the mode collapse problem is addressed.
Right. And so in some sense, you're saying that the flow-based MCMC sort of sits in between your forward and backward model in a way that might help you solve mode collapse, but not require full ahead of time MCMC.
I would say it doesn't solve mode collapse, but if it lets you improve Monte Carlo relative to something that didn't incorporate the normalizing flow.
Yeah.
Basically, you sample from your flow, but the flow will have some difference from the true distribution. And so, you know, you're sampling from a distribution close to the thing you care about, but not quite the same. And so you can modify that by, you know, incorporating that into a Markov chain such that you reject things that are too far out of distribution, and you get something that's statistically exact.
Right.
Yeah.
So it uses both the MCMC for statistically exact and getting getting better proposals using the flow.
Mm-hmm. Yeah.
Good. Wonderful. Well, thank you very much. That was great. Thanks to everyone who came. We're a little bit over time, but let's thank Gavin one more time. And great to see you. Hope to see you in person at some point.
Oh, that'd be great. Yeah.
Yeah, that would be great. I'll actually